Hello,
Yes, sir.
can I start?
Yes, sir. Yes, sir.
Okay. So, good morning to you all. So, yesterday we were discussing about the Bishop's method, the Bishop's modified method. So, for determining the factor of safety, and we also have seen how to derive a slope stability equation for determining the factor of safety. But we missed a lot of things in between, so I will try to cover many of some internal things, like what is the fundamental assumptions involved in each and every method. Because if you refer to any of the soil mechanics book, most likely all the methods end at Spencer only. So most of the books, even if you take the BM Das or the Bevels book, so all the books, most of the books are giving the information only up to Spencer method, and that is also an extension of Bishop's modified method. But later, several researchers have tried to work on the more complex problems by taking into account the normal forces and the tangential forces acting on the slides. Okay, that is one fundamental thing. Then another important point is, if you look at carefully, most of the slip circles are circular in nature, but in reality, it is not only circular, but it could be even non-linear also, because we have also seen transition failure for infinite slope. So, but what if a slope consisting of circular along with the transition, or circular along with other mode of or any other shape? Okay, so which is typically a non-linear shape. So it can be designated neither as a circular nor as a complete transitional. So therefore, people started working on with the development of sophistication of the computer programs. So they try to derive the more complicated equations for understanding or for determining the normal forces and the tangential forces. So for example, if you look at this schematic, so this also gives a free body diagram of a one slice, where here you can see EI and EI plus 1, which are acting in the inclined direction. So which is originally true, they cannot be in the horizontal direction. But when you resolve the EI into normal and component, then they will become horizontal and vertical, because this resolution is required in order to satisfy the equilibrium equation in the vertical as well as in the horizontal direction. So today, let us talk about another method by Morgan, Stern and Price. This is the more complex method. Without the aid of computer program, one cannot able to solve any slope equation with the help of Morgan, Stern and Price. Okay, so it is a general method of slices developed on the basis of, again, on limit equilibrium. Almost all the methods are on the basis of limit equilibrium, and this method, like what we have seen in this method, so it satisfies two equilibrium equations, that is equilibrium of forces and equilibrium of moments acting on individual blocks for both circular and non-circular slip surface. So it is important to note that in all previous analysis, we were considering only the circular slip surface, but this Morgenstern and Price method considers so both circular and non-circular. The another advantage of this method is, if you look at the surcharge load, there also there is some kind of a constraint put over by the different people. So it has to be only uniform load, or only point load, or only the horizontal surface. But what if the load is variable, and what if the load is some function of a mathematical equation? So all these things were taken care by the Morgenstern and Price method. So if you look at carefully, so I can summarize in this way. As per the Morgenstern and Price method, the slip circle may be circular, may not be circular. This is the important point. Second, this method considers uh, the interslice forces on either side of each slice. So they will try to determine the interslices forces, and based on which the factor of safety will be calculated. The third important point is it also consider the surcharge as a function of the mathematical equation. So it is immaterial whether it is a uniformly distributed load or point load or any other type of the loading, it is immaterial. So these are some fundamental assumptions involved in Morgenstern price method. So first of all, dividing the planes between blocks vertical. Line of action of Wi, as you can see from this schematic, passes through the center of the ith slice. So this is ith slice, passes center of ith segment of the slip surface represented by point M. The normal force Ni is acting so in the center of the ith segment, because these assumptions also nowhere, so one can able to find corresponding to previous all methods so far we have discussed. Inclination of forces Ei acting between blocks is different on each block delta I at slip surface endpoint, that is delta is 0. So these are some assumptions. And as per this method, the equation of the factor of safety is remained same. So whatever the Bishop's method, the factor of safety equation is there, same method. But if you look at carefully, that equation encompasses two things, delta T and delta M. That is the interslice forces in the normal direction as well as in the tangential direction. So the crux of all remaining problems is how accurately you could able to measure or quantify the tangential forces and the normal forces acting on each and every slide. Okay, so as per this method, so they evolved with a new function that is called as x is equals to lambda into f of x into e. Now what is x and what is e? So x is interslice shear force. They represented everything in a mathematical functional form. And interslice normal force is E. Interslice normal force E. Interslice tangential force is X. And some arbitrary function f of x. Then some scale factor for the assumed function. So lambda associated with the f of x. So this is one form of the equation so that they assumed, and using this one they try to determine the interslice forces. Now if you look at this one here, the almost all the parameters are unknown. We do not know x, we do not know lambda, we do not know f of x, we do not know e. So here unknowns are the factor of safety, which is the fundamental thing one has to be determined, lambda, that is scale factor, normal force on the base of the slice, that is either P or N, both are same, E, that is interslice shear force, and the location of the interslice force. These are all unknowns. So once these unknowns are calculated, so the X, the interslice shear force can be calculated. So using this equation. So in order to independently solve this equation, so they have considered equilibrium equations separately. So there is also some amount of work has been done by Friedland and Krahan in 1977. So they have also considered only the mathematical equation which is proposed by Morgenstern. So this is very complex method, and these steps which have been shown here are intermediate. Okay, so this is I'm giving only for your understanding and explanation. If you really want to look into it, the derivation of all these equations, so it is a huge paper. Okay, so I'm just giving some highlights. So all these slides are presenting just highlights of Morgenstern and Price method so that you will better understand. Now on this equation, Friedland and Krahan, so they did work. So to compute the normal force and the shear forces. So they expressed the normal force P, so in terms of the factor of safety. So if you look at this equation is remains same as the equation which is proposed by the modified Bishop or modified Bishop's equation. So as for the Friedland and Krahan, so the normal force P can be expressed in this form. can be expressed in this form. So here also there are to further determine the other parameters. Now they further went one step ahead to define the factor of safety in two terms. One is with respect to the moment equilibrium and another is with respect to the force equilibrium. Okay, so this is the form of moment equilibrium and the same equation, the moment equation for non-circular slip surface. While if you want to convert this equation to be valid for the circular, then these are the assumptions you have to make, and this will be transformed to the circular slip surface. So this bottom one is valid for circular slip surface, while this equation is valid for non-circular slip surface. Now, but this is the factor of safety equation with respect to the moment equilibrium. Now, there is another equilibrium equation, that is the factor of safety with respect to force equilibrium. So this is the with respect to force. So there is a distinction. This is the moment equilibrium and this is force equilibrium. So we can see the difference between the moment equilibrium and the force equilibrium. Now, how these equations will be solved in order to obtain the normal and tangential forces acting along the vertical surfaces. So on the first iteration, XL and XR. So if you look at this normal force equation, there is an XL and there is an XR. Okay, on either side of the slice. On the first iteration, XL and XR are set to 0. On subsequent iterations, the horizontal interslice forces are first computed using this equation. So keep on substituting and keep on assuming some values. But initially, the XL and XR values are set to 0 and the normal forces are computed, and thereby the factor of safety is determined. Okay, it is not that much easy as I say. Okay, so it is not that much easy. Please try to understand. This is only to give you the glimpses of the most complicated form of the equation. That's it. So then the vertical shear forces are computed using an assumed lambda value and assumed function f of x. So here you can see the f of x could be from this schematic a sine function or a constant or any other mathematical equation, doesn't matter. And there is also a relationship they proposed, which is between the factor of safety versus the lambda. So that means, so you need to initially define the loading condition, the f of x, say in the form of a sine or the constant. Constant means the horizontal surface. Sine means some variable load. So then assume again the value of the lambda and try to determine the factor of safety. So once XL and XR are determined, so P on the base of each slice is then calculated. Determine the normal force, that is P. So here don't get confused again, the normal force, this is the P. Okay, so in Bishop's equation also, what we have done, we have substituted FR and we have substituted I think FT. So into the one of the equilibrium equation, that is vertical equilibrium equation. Then we have simplified everything into the normal force, that is N. So here also same thing. So we have taken the same form of the equation. So this P is normal force. So that means for an assumed the normal forces acting all along the slices, so that is developing beneath the slice is calculated. Okay, which otherwise initially in all the methods we were simply assuming no interslice forces. If there is no interslices forces, then simple equilibrium equation. So once XL and XR are determined, the normal force P on the base of the each slice is then calculated. So value of lambda for which Fm is equals to Ff can then be found iteratively as shown in the figure. So keep on assuming the value of the lambda and keep on determining the two separate the factor of safety equations. One with respect to the moment equilibrium and another with respect to the force equilibrium. So whenever Fm is becoming equal to Ff and corresponding to which, so the lambda and corresponding to which the factor of safety is the factor of safety of that particular slope. So here some fundamental things you must understand from this simple diagram. So this is also the factor of safety versus lambda. So if you look at any literature, you find more than a dozen variety of methods which are useful to determine the factor of safety. So we know only the Bishop method, so based on the method of slices, but there is ambush method, Sharma method, Morgenstern and Price method, Spencer method. There are several methods. Okay, so this is the fundamental distinction between all these methods. Bishop's and Ambo's simplified methods ignore interslice shear forces. Now, what do you mean by ignorance? So, ignoring the interslice shear forces, that is putting the lambda is 0. When lambda is 0, it indicates that these methods interslice shear forces and satisfies only the moment equilibrium. Thus, lambda is 0. And any other method which inherently takes care of both moment and force equilibrium equation, then so the will meet somewhere at this point. Okay, so this intersection indicates, this intersection point indicates that particular method has taken into account of the force and moment equilibrium, both moment and force equilibrium. So this intersection, even Spencer method also satisfies both force and moment equilibrium. So this is the most complicated Morgenstern-Price method. Almost Ambo's method, Sharma's method, Morgenstern-Price method, Spencer method, almost all the methods considers only this kind of analysis. So once you are knowing for one method, remaining all methods you can easily able to understand. Okay, so more than that, you don't need to aware of anything about it. Now let us try to understand how the factor of safety fluctuates when the slope is constructed on saturated clay. Okay, so that's what all about the derivation of the factor of safety equation. Now let us try to have a little deep understanding about how the factor of safety varies. So here I have taken a small example and the soil is under undrained condition. So when the soil is under undrained condition, the friction angle is 0. So this is the fundamentals. So once CU, okay, that is CU. Now suppose if you take any point P, so beneath an embankment, now the embankment cannot be built overnight. So it is some time bound phenomenon. So if you look at this diagram, so this initially increasing with time indicates this is how the progress of the embankment is taking place. At time T1, the construction of the embankment is over, and thereafter the load is remains same. The height remains same, load remains same. So now what happens as you are progressing the construction of the embankment? What happens to the shear strength? Now before you are talking about the shear strength, there is an inherent relationship between the shear strength versus the pore water pressure parameter. So here the shear strength, this is average shear strength. When you are increasing the height of the embankment, so the value of the tau, that is shear strength, will increase linearly with time up to T is equals to T1 and remains constant thereafter. So one important thing is, when I talk about all these diagrams are with respect to point P. no other point, only the point P. So as you are increasing the height of the embankment, there is an increase in the shear strength of the soil. But how the shear strength is getting increased? Because unless something is happening inside the soil, the shear strength cannot increase. Now that can be correlated with the increase or decrease of the excess pore water. So as we understood from the previous slide, the soil is saturated. So therefore, the initial pore pressure can be designated as gamma W into H. Gamma W into H. Now since it is a fully saturated, so we have an assumption from the triaxial testing, and assumption from the consolidation is when any soil sample is fully saturated, the entire load is initially taken by only the water component, not by the soil component. Conversely, as you are keep on increasing the load or imposing the load, so consequently there is an increase in the pore water pressure. Increase in the pore water pressure. So it reaches a peak when the embankment height reaches its maximum. The increase in pore water pressure reaches a peak when height reaches the maximum height, as we can see here. So there is an increase in the delta. Now, once the loading become constant, because of this surcharge load, the water tries to dispel or expel from that particular region, and consequently, so there is a decrease in the excess pore water pressure. As there is a decrease in the excess pore water pressure, so the obvious consequence is increase in the shear strength of the soil. As you can see, sigma dash is equal to sigma minus u. So effective stress is equal to total stress minus pore water pressure. So as you are keep on decreasing the pore water pressure, so the obvious effect is increase in the effective stress. So increase in effective stress means increase in the shear strength. So the decrease in the pore water pressure happens until it is reaching again the initial pore water pressure condition. That is gamma W into H. Now this condition is the most critical. In terms of the slope stability, this condition is the most critical. So when the pore water pressure is keep on increasing, so this can cause the excess lateral thrust leading to the failure of the slope. This is one of the fundamental reasons most of the slopes fail in saturated clay, because of this development of excess pore water. So this is a pore water pressure, and correspondingly there is increase in the shear strength. As we can see here, up to point T1 the shear strength is remained constant, and when there is a dissipation of the excess pore water pressure, and consequently there is an increase in the shear strength within the soil sample. Now suppose if you want to understand how the factor of safety increases, so initially as you are imposing the load, so there is a decrease in the factor of safety with increase in the pore water pressure. As pore water pressure decreases, the shear strength increases, and there is an increase in the factor of safety. So this is what exactly happens. So within the ground, when you build any structure on the natural ground, especially this is on saturated clay. Okay, so now this gives a small glimpses that the factor of safety is not constant during the construction of any earthen structure. Okay, any earthen structure. Now you may ask a question: can this be valid for any other soil mass? For example, let us take a dry soil. So for dry soil, is there a possibility of the variation in the factor of safety? So the answer may not, because when you impose any surcharge load on the dry soil, it can go only settlement, not consolidation. Okay, because there is no dissipation of the pore water. Since no dissipation of the pore water pressure, so there is no possibility of increase in the factor of safety. So in that case, it becomes almost constant. Now this is another case where in the previous case we are keep on imposing the load on the saturated clay. Now let us try to understand. Suppose what happens to the factor of safety when you make a cut. So when you make an vertical cut, so this is what. So initially the ground surface is horizontal. So now when you are keep on cutting, so during the advancement of tau, that is shear strength, on the failure surface increases. The shear strength on the failure surface increases. How? So this we need to understand. Okay. Now here also try to understand. When you are making a cut can be in the vertical, perfect vertical with a slope of 90 degree or having any slope angle, maybe gentle or maybe steep. Maybe steep. Now when the surface is horizontal, here the kind of the geotechnical condition prevails is a different. But when you are making the slope or when you are cutting it, so the original ground condition slowly transforms from one condition to the another condition. So initially it is under consolidation, self-weight consolidation. But when you are progressing for the cutting, the consolidation problem transformed into the slope stability. Okay. So when there is a slope stability, so then how the shear strength and shear stress are varying as you are progressing the advancement and the excavation. So here also you can see. Now in the previous case, when you are imposing the surcharge load, there is an increase in the surcharge, the excess pore water pressure with increase in the overburden pressure. But in this case, you are doing in a reverse way. So reverse way. So you are removing the load. So there the pore water pressure is positive. But when you are removing the load, the same pore water pressure becomes negative. So the same thing can be seen. So as you are removing the load, so the pore water pressure is becoming the negative. So it is becoming the maximum negative when you are cutting to the lowest depth. Then once you are leaving it, so it also again allows kind of a dewatering or expulsion of the water, and thereby the excess pore water pressure again reaches to the zero or the initial condition. So this is the profile of the excess pore water pressure. So because of the excavation, the effective stress at point P decreases because you are removing the overburden pressure, which will induce a reduction in the pore water pressure. So at time T2, delta U will be 0. At time T2, delta U will be 0. That is, it is reaching to the initial condition. Now here you can see how the shear strength of the soil is decreasing as you are advancing for excavation. So initially there is some amount of the shear strength. With decrease in the pore water pressure, there is a decrease in the shear strength because this is removal of the load. Then correspondingly there is a decrease in the factor of safety also. So as there is a decrease in the shear strength within the soil, consequently there is a decrease in the factor of safety. T is equals to T2. So this is a small example that demonstrates how the factor of safety varies. So when you build any kind of an embankment on a saturated glacier. Now other conditions also you should understand. What do you mean by the long-term and short-term stability analysis? So this slide will give you glimpses about what kind of conditions to be considered for short-term stability and for the long-term stability. So this is an embankment. This is an earthen embankment with a clay core. So this is a clay material. So the clay material is less permeability. Now in case of the short-term stability, so short-term means we haven't given enough time for water to dissipate from particular area. So consequently, when you do not allow the water to dissipate, the kind of a condition that prevails is an undrained condition. So the undrained shear strength parameters can be designated as Cu and Pi U. So for all short-term stability, slope stability analysis purpose, one must use the undrained shear strength parameters, that is Cu and Pi U. And how do you obtain these Cu and Pi U? Either you can conduct by conducting the unconsolidated undrained test or the consolidated undrained test. Okay. Often you may see that many of the people are simply conducting the UCS test and they are using the value of the Cu, but which is not true. Okay. So the UCS will always give you the least possible shear strength of a soil. It is only the indicative test. And the UCS is mostly important for the transportation engineer, not for the geotechnical engineer. So as a geotechnical engineer, you always has to advise to conduct either UU or CU. So never ever encourage the shear strength determination by UCS. Okay, UCS is typically valid for the transportation engineering, not for the geotechnical. Now, when you are conducting the unconsolidated undrained, what you are going to do? You are going to impose three kinds of the confining pressures and keep on applying the deviated stress. And in case of the UU, you are not going to measure any kind of the pore water pressure. But in case of the CU, one can able to measure the pore water pressure. In fact, when you conduct the CU, two variety of shear strength parameters can be obtained. We can obtain the undrained and drained. So if you do not allow or if you do not measure the pore water pressure parameter, then what we get is Cu and Phi U. So just try to recall our shear strength analysis. And when you allow the pore pressure parameter measurements, then what you get is effective stress parameter, that is C dash and Phi dash. So during the short term stability, one should consider total unit weight of the soil, that is bulk unit weight of the soil. And the kind of the stress analysis is called the total stress analysis. Change in pore water pressure totally dependent upon the stress change. Next, the long term stability. So in the long term means we allowed water to completely dissipate from that particular location. So once there is no water means that particular condition is called as a drained condition. Drained condition. So here for long-term slope stability analysis purpose, you should use the drained parameters. That is CD. D designates drained. CD or C dash or pi D or pi dash. And these parameters can be obtained by conducting the consolidated drained triaxial test or consolidated undrained test with pore water pressure measurements. And effective unit weight of the soil, that is gamma dash or gamma submerged, and called as effective stress analysis. So change in pore water pressure independent of the stress change. So that's all about the slope stability. Now, so let us have a small glimpses about what are the different methods that are available in the literature or who did work on deriving the factor of safety equation. Then what is the fundamental assumption and what kind of the failure surface that they have considered, and what is the equilibrium equation that is considered, and what kind of is required to compute. So if you look at the efforts were constantly made since 1927 to even up to more than 2002 also. If you look at Mikulovsky method, it is proposed in the year 2002. Okay, so the analysis of the slope stability is evolving almost extent of interslice forces is 0. Okay, and considers circular slip failure and only moment equilibrium. And we just need only calculator to determine the factor of safety. Then Bishop method. So in the year 1955, there are Bishop simplified method and Bishop's modified method. So Bishop simplified method, EI and EI plus 1 are all collinear, and this is normal forces, and XI and XI minus XIJ plus 1 is 0. No, here also no interslice forces. Then circular, moment and calculator. Then Bishop's modified method. So EI and EI plus 1 are collinear, J is equals to 0, circular, moment, calculator. And Morgenstern Price method, relationship between E and X in the form of X is equals to lambda f of X into E. Okay, so this is a relationship between the normal force and the tangential force related to the surface loading and scale factor. So is a function which is lambda is a scale factor. Lambda is a scale factor. Here also, in fact, Morgenstern is for any shape, not for circular, non-circular, any shape. And the equilibrium equations all, not only moment, even force and moment both. And we need a computer. So then Spencer method, almost very similar to Morgenstern and Price method. So it also considers any shape of the failure plane, and it also considers all form of the equilibrium equations. We need a computer. Then Bell's method, then Ambo method, then okay, here the Sharma method also includes some seismic forces. So this is additional, and Ambo method is only for non-circular, and it only considers the horizontal force. Okay, so you need to have a fair idea about all these things, because so in real life, say for example, you may have to go for non-circular, or like we may have to go for Ambo method, where there is a prevalence of only horizontal forces and there is no vertical forces. And if you look at carefully, most of the geotechnical structures, there are prevalence of uh, some only exclusively horizontal forces without any vertical forces. So you need to take your own judgment what kind of a method I should use it. Should I use the advanced methods like Morgenstern and Price, or should I go for condition based analysis or field based analysis? Okay, so this should give you a good idea about what method should I pick it to determine the factor of safety. So it's not that key the method is available in the computer, then I will do some kind of analysis and determine the factor of safety. No, it is not. Okay, so this is the fundamental thing. And we have also seen that like Bishop and Morgenstern method, it is valid only for the drawdown condition. Similarly, Spencer method also valid only for the drawdown condition. So these methods cannot be in general used. Again, the other conditions also you must take into account. So these are some assumptions. This is summary about the other assumptions. Ordinary method of cells, interslice forces are neglected. Then Bishop simplified or modified. Resultant interslice forces are horizontal. There are no interslice shear forces. Then Ambo simplified method. So resultant interslice forces are horizontal. An empirical correction factor is used to account for interslice shear. If you look at carefully the hierarchy of the oldest method to newest method, so everybody is attempted to overcome what was assumed in the previous method. So here it is clear. Bishop assumed there are no interslice forces, but Ambrose has overcome by assuming an empirical correction factor. Spencer method, the resultant interslice forces have constant slope throughout the sliding mass. The line of thrust is a degree of freedom. Then Chugg method, same as Spencer method, but with a constant acceleration of arc, so constant acceleration force on each slice. Then Morgenstern Price, the direction of the resultant interslice forces is defined using an arbitrary function. The fractions of the function value needed for force and moment balance is computed. So Fredland and Crank, in fact, both the methods are same. Then corps of engineers, the resultant interslice force is either parallel to the ground surface or equal to the average slope from the beginning to the end of the slope. Then Lowe and Karafiat, the direction of the resultant interslice force is equal to the average of the ground surface and the slope of the base of the each slice. Sharma's method, the shear strength criterion is applied to the shears on the sides and bottom of the each slice. Okay, so what I mean to say is you need to have fair understanding about the assumptions of these methods to pick up the validity of that particular method for that particular field condition. Okay, so suppose if I do not have shown these slides, like what is the method and what is the fundamental assumption, then there is an obviously in your mind that I can use any of these methods for any of these conditions, or you have to again so churn lot of literature to understand what kind of a method I should use so that the factor of safety that I'm going to get is a reliable one. Okay, so try to understand most of the failures can happen by picking up even the wrong method of analysis. If you look at carefully, if you understand truly as a geotechnical engineer, if you pick up the wrong method, then though the factor of safety, say for example, you are on the verge. When I use say Swedish method, but my factor of safety is say 1.1 or 1.2. But if I use another method, say Spencer method, and I got the factor of safety of 0.95, it indicates that it will fail. But the mark the slope stability analysis. So this is a summation about others. A method, force balance in vertical direction, force balance in horizontal direction, and moment balance. Ordinary method of slices, force balance in vertical yes, but in horizontal no, moment balance. Bishop's method, so force balance in vertical and moment. Then Amboss method, for only force balance, no moment balance. Amboss general method, so force balance and moment balance. So Spencer method, everything. Chuck's method, everything. So as we can see. Okay. So this is the assignment that I have given you. So this is all about the slope stability. So whatever today I have presented is which is additional extra. So these information is not available in the books. The Morgenstern price method is an advanced method which is currently used by almost everywhere. Nowadays nobody is going to use the Bishop's method or something else. Okay, we have still 10 minutes. If you want to ask any question, you can ask me. And regarding your big project also, one additional thing I have added, as you can see here. So yesterday we were discussing about rapid drawdown condition, rainfall on the slope, progressive failure or stage loading, seepage analysis for steady state condition and transient condition, variable phreatic surface, liquefaction, flooding condition, water table coincides with the ground surface. Then there is another thing called as a strain hardening or strain softening. Okay. If you want to ask me any other question, you are most welcome.
Sir, what is the practical significance of long-term analysis and short-term analysis?
Long-term and short-term analysis means so for any slope, the worst condition is during the construction. So this is what you read. So end of the construction is worst condition for any construction. So therefore, you need to determine the factor of safety corresponding to end of construction, which is nothing but the short term. Because the end of construction is a dynamic condition, while the long term is a static condition. In the dynamic condition, there is a variation in the pore water pressure. So there is an increase or decrease in the excess pore water pressure, and which is an obvious effect on the factor of safety. So this leads to variability in the factor of safety. Now the first thing is that when the factor of safety is varying, is the variation is taking you to the least factor of safety where you are going to encounter the failure. Okay. Second, once the factor of safety is stabilized, is that stabilized factor of safety is sufficiently high and which is in compliance with the codal provisions. Okay, for example, say IS code recommends a factor of safety of 1.5. Now, is this corresponding to long-term stability or the short-term stability? Okay, so this is what you have to understand.
So like we have done long-term analysis on some slope,
Okay.
and due to flooding condition came there. So the factor of safety which we considered would not be sufficient and the slope will fail.
May fail, may not fail. Okay, may fail, may not fail. That depends upon other conditions that may prevail during the flooding. because normally if you look at any embankment of a road or railway track, none of these embankments are designed for any flooding condition. Okay, so this is one of the reason they during the each and every flooding condition they will simply breach.
Okay, sir.
But we have to understand when there is a flooding, either heel portion is weaker or toe portion is weaker. So this is to be ascertained.
Sir, in cases where there are frequent flooding, then we will go for short-term analysis only.
Instead of going for long term or short term, when there is a flooding condition, what happens to the stresses inside it, you have to understand.
Okay,
Okay,
sir.
when there is a flooding,
Yes,
are
sir.
you allowing the flooding condition to increase some kind of the stresses, or are you relieving the flood itself?
Okay, sir.
Okay, so for example, seepage is a imminent phenomenon. By no means you can avoid the seepage.
Yes, sir.
But when the seepage exceeds certain value, then there is a danger. Okay,
Yes.
but we cannot in total eliminate the seepage.
Okay, sir. So depending
Okay,
upon the conditions there, we have to take the measures and values.
no, you need to assume all these conditions and envisage that what happens if a seepage exceeds this value. What happens to the factor of safety? Which otherwise, what is the point in doing the factor of safety analysis for all these taking into rapid drawdown or rainfall or the progressive failure?
So we will analyze all the situations and the least factor of safety will be then provided.
May not be all the cases, from case to case. See,
Okay.
for example, you take the railway track or the road.
Yes, sir.
So among these conditions, which one can prevail?
Uh, Sir, only in the rainy season seepage can occur.
Okay,
Drawdown will not be there.
correct.
So we'll analyze for this seepage mainly.
But seepage has to happen. There has to be ponding of water.
Yes, sir.
So there is no ponding
Yes, yes, sir.
because so in that condition only flooding is good enough.
Okay, sir.
Okay, and other condition is like the strain hardening and strain softening. This is with respect to the material.
Okay, sir.
So we may analyze for the flooding condition, or we can also think of what happens during the rainy season when the water level is reaching to the ground surface.
Okay, sir.
Okay.
Okay, sir.
So for example, variable phreatic surface. So for all reservoirs, you must analyze for variable phreatic surface because your
Okay.
water level keeps on increases, decreases. Na?
Yes, sir. Yes, sir.
So during the rainy season, there is a full reservoir level, and
Yes,
there
sir.
are it constantly decreases. So
Okay.
as the water level recedes, there is a in the phreatic surface also.
Okay, sir.
So then what happens to the factor of safety? And at the same time, there is a seepage also. So then what? Yeah, others.
Sir, in
Most of the
Bishop Morrison,
yeah, yeah,
in Bishop Morgenstern method,
yeah,
that D which we were using, is that the same as Taylor's depth factor?
yeah. Same as the depth factor.
So that depth of hardship divided by height of soil
Yes,
is
yes, yes, yes.
okay.
Sir, in this assignment which you gave, this statement of problem one,
Yeah,
we have to take an example of a hypothetical this slope and do the further analysis.
yeah, yeah, yeah. Take some hypothetical condition and do the analysis and try to understand how to do it.
Means according to the problem, which method is appropriate and other things which fact is to be analyzed like that.
Correct.
Okay.
So this will give you two things. One is how to understand the realistic condition. Second thing
Yes.
is how to pick up the most appropriate method.
Okay.
Yeah, others. Most of them are very silent. Yeah, any questions from others? Why you are so silent?
No, sir.
We should ask as many questions as possible. So that you will learn, I will learn, others also will learn.
Sir, could you go to that slide where pore water pressure and strength relation was given in the form of graph?
This one?
Yes, sir.
Yeah.
Sir, here in the first graph, when pore water pressure is increasing,
Yes.
shear strength is constant. How is that? It should decrease now.
Shear strength. Means why do you expect there is a shear strength?
Because if pore water pressure is increasing, that means effective stress is reducing. Sir, your voice broke.
Okay, what is the equation for tau in this case?
C plus sigma tan phi.
So C plus sigma tan pi.
So this is for clay. So phi will be 0.
Yeah. I'm coming to the same point. Thank you.
Yes.
So, but what I told, this is a saturated clay. Saturated clay means pi is 0. So whatever remaining is only
Got it.
whatever whatever remaining is tau is equals to Cu.
Okay, fine, sir.
Yeah. So no problem. Good. You have to understand all these things.
But then, sir, it should not increase also.
But what about Cu? Cu is increasing, na? See,
So,
when you do any triaxial testing, so what is happening? What did I say? The cohesive material is becoming the frictional material with expulsion of water.
correct.
So that means after some time, when the whole pore water pressure gets dissipated, there should be some pi value.
Some phi value will be there.
That means your shear strength equation will be transformed from initial tau is equals to U to C plus sigma tan pi.
Yes, sir.
So that means this is how the shear strength improves.
Okay, sir.
So you can connect this to the Mohr circle diagrams. How the slope is increasing as you are going from UU to CD test.
Yes, sir.
Yeah, others. Any other question? Okay, so no problem. So happy Dasara to all.
Thank you, sir.